Welcome to Lesson 5 of the refresher course for calculus for teachers. What we've done so far, let's see if I can move this a little bit over to the left so that you can see it. Looks like I'm going to have to, oops. You can tell none of this is edited. Let me justify that a little bit so we can see it a little bit better. What we've done so far, Lesson 1, we did limits, continuity, and an introduction to differentiability. Lesson 2 was differentiation, techniques of differentiation, how do you take derivatives. Lesson 3, we covered applications of the derivative. Nice thing, see, we're not edited. Applications of the derivative. And Lesson 4 was Introduction to Integration that we did last week. I understand at the end of last week some of the tape messed up a little bit, so we're going to look at slope field again at the beginning of this week, and that's where we're going to start the lesson today. One of the things that was advertised for this course was that we were going to be looking at calculus sort of the new way. The reformed calculus movement has done some things to change calculus, and I'd like to spend just a little bit of time talking about that. One of the things, when I took calculus a few years ago, the thing to do in calculus was to do it analytically, do everything by hand, about the only thing we got to look up in the chart in the back of the book was the trig functions. One of the things that I've tried to do in the lectures we've been having recently are also work a little bit more on graphical interpretation of the data, verbal interpretation of the data, and numerical interpretation of the data, of the information, with a thrust in technology. And of course, I've been using the TI-83 quite a bit. The TI-89 is out there. It is I think, going to probably be in a couple of years the calculator that most people are going to be using on the AP test, or at least that's my opinion. I'm not real sure that that's going to be absolute, but it seems to be that. What we're going to do today in Lesson 5, and I've got a couple of things highlighted here to emphasize it, what the new reform calculus is doing. Today we're going to look at slope fields a little bit. We're going to go to integration techniques. Now, when I took my second semester calculus course on integration techniques, this was what was 90% of the course, plus a few other things, trig substitution and a few other types of integration that we're not going to cover today. That right there was the meat of the course. That was by far the majority of the course. I went back and got my 1960-something calculus book, and I found 1.5 pages on exponential growth and decay in the calculus book. One of the things that is happening to the calculus now is that we are moving, it seems to me that we're moving a good bit of what used to be called the differential equations course back into lower level calculus, and maybe a little bit at the end of Calculus 1, some at the beginning, or some throughout Calculus 2. But techniques that are things that I learned in my differential equations course, or courses outside of the calculus, slope fields, which we're going to talk about, exponential growth and decay. We did a good bit of that in pre-calculus, but obviously not concerned with the integral or the derivative. Population growth with the logistics curve, and numerical methods, Euler's method. So one of the things that is happening with calculus these days is we're getting a little bit of that push down, that same stuff, that same concept that Algebra 1 and Algebra 2 are being pushed down into the middle school. Well, some of the college courses are having the same thing, especially those that are adopting the reform calculus, that are embracing the reform calculus movement. So those are the topics that we're going to be talking about today. I shouldn't have moved it, I guess. Those are the basic things that we're going to be talking about today. And then for the rest of the course, lessons 6, 7, and 8, next week, see if I can get that more in the center of the screen again. Lesson 6, we're going to be looking at applications of the integral. Those of you that remember the shell method, the disk method, all those nice methods of finding volumes, and quite a few other little applications, some interesting applications. We're going to look at those next class. Lesson 7 are those absolutely adorable sequences and series. Lesson 8, we're going to look at parametric and polar equations, and we're going to have a discussion of the free response type question from the AP exam. So that's where we've been, and that's where we're going. And I got the right button on that one. And the first thing I want to do is talk about slope fields for today. Slope fields have to do with taking an equation that you know is the derivative and finding its original function, or taking an equation and finding its antiderivative. Now, one of the things that I asked that you do towards the end of last class was to see if for your calculator, I think the TI-89 has it built in, but the 83 does not, could you find an equation, a program for your calculator that does slope fields? I've got one here. Oops, that's not what I want. Okay. I want to go to the document camera. Nope. Okay, help me on this. How do I get to this one over here? We'll be there in a second. There we go. There we go. I've got a program in here called Slope. There are several programs out there. I don't know the origin of this program. It's just a program that was out there. There's no way that you're going to be able to copy it and enter it in a short amount of time. It took me about an hour to enter the whole program in when I did. But the program, what I would like to do is spend a few minutes. I know a lot of you are taping this, so that what I'm going to do is show you the code for this program, and then you can copy it down, and then later you can pause the video and enter it. So what I'd like to do is to show you the coding a little piece at a time. Certainly don't try to change it, to put it in your calculator right now. It's going to be too difficult. And I will talk with the powers that be to see if we can also get this on the internet page. Now, I know for a fact this is not the only slope field program out there. There's another one that's pretty good called Slope FLD, and I've probably seen 2 or 3 others at local meetings, at NCTM meetings, things like that, where people share. This one is fairly quick and efficient, and it's the one I like to use. It's quick in its graphing. So that's the program. If you want to go back and look at some slope field stuff after you've viewed the video, please do that. It will take you a good while to enter the program in. Excuse me. For those of you that do not know how to enter the program in, it's slow. It's not difficult, but it is slow. Down at the very bottom below the 1 key, the 0 key, if you hit second 0, it will give you a catalog, and that catalog has a whole list of the commands that you saw with the uppercase and the lowercase letters, and you have to search alphabetically through that list to enter the particular command that you want. So it's tedious to enter a program. It's a lot easier to find somebody else that already has it and download it. Let them do the work, and you just share in the profits there. Okay. Well, to work this program, we have to talk about what we're going to do. Now, the equation that I'm going to put in, the equation that I'm going to look at is y1 equals x. Now, let's do a little bit of analytical stuff here before we look at the slope field. But what we've got is basically y equals x as a program. Well, as an equation. What we've really got, let me write that bigger. What we've really got is y prime equals x, or dy dx equals x. And when we have that, what we want to do is take the antiderivative of it. We want to find what the antiderivative is. Now, we talked about the antiderivative the last class, and of course the antiderivative of dy dx is going to be y, and the antiderivative of x squared is going to be some function whose derivative will give us x. Well, if we take the integral of both sides with no limits on it, we're not doing a definite integral here, we'll get a y here, we'll get an x squared over 2 here, and of course plus a constant, because remember, when we take the derivative to go back, the derivative of that constant is going to end up being 0. I'm sorry. Thank you. I'm as lazy as my students are on that. So, one of the things that we're going to be talking about with the derivative, with the slope field, is this c. Because depending on what the c is, we might have x squared over 2 plus 1. We might have x squared over 2 plus 5. We might have an antiderivative of x squared over 2 plus, minus 7. And of course, this number right here will just take the original curve, whatever the original curve is, whatever the absolute answer is. I'm not sure that there is one. We'll take it and either slide it up the y-axis or slide it down the y-axis, depending on whether this number is positive or negative. It's going to be a vertical shift, either up or down. So, if we look at using this, okay, I'm going to go to Program. I'm going to arrow up to where I find slope, and I'm going to run the slope program. The name of the program is slope, and I'm going to run it. I've already run it. You can see it. It generally takes a little bit longer to graph than that. But what I've got here to show you how it works is all these little dash marks all around the program. Then I've got the line y equals x, and I've got a parabola in here. Okay. Now, what we're going to do is put these things in one at a time, but what we want to do is see that all these little dash marks are in fact your slope field. Now, sometimes instead of a slope field, it might be called a direction field or a tangent field. These little line segments are tangents, and they're tangents that are created by finding what the derivative is at a particular point. Now, if this is the line y equals x, let's look at how y equals x turns into this slope field. If we look at this point down here, if this is the slope, well, the slope is a negative number, and it's a pretty steep negative number. Notice all of these tangent lines are pointing down. It's a negative slope on all of these tangent lines. Now, what is happening as this line, y equals x, gets less and less negative, or gets closer and closer and closer to 0? Then it tells us that the slope is getting less and less negative, if you will. And you can see that the little tangent lines are starting to flatten out here. Instead of being vertical, they're starting to move up. The slope is increasing. It's still a negative number, but the slope is increasing towards 0. Then all of a sudden it hits the point 0. And at 0, we've got all these little tangent lines that are horizontal. We have a slope of 0. Then as we go to the positive numbers, look what's happening to the little tangent lines. The tangent lines now switch over to have positive slopes. So we can see that the little tangent segments in here, these little segments, are reflecting the value of the y equals x, as y equals x is the differential equation, or the equation that tells us the derivative of the equation that we're looking for. Now, I've drawn this one in here. I've gotten this one drawn in here just to show, it's not exact, but just to show a curvature here. How do we find the antiderivative with a slope field? Well, you sort of pick a point that you want to start. That would be your initial condition. If you remember your initial condition from the last set of classes, we have a whole set of equations that we can have with the plus c. Initial condition sort of tells us where to start. And you can see if you sort of trace a little section, you come down, you flatten out on the tangent line. You're tracing the tangent line. You've got a little parabolic look. Now, obviously this parabola is not a really good fit for those other little tangent lines. It doesn't fit it well, and I just realized why. There's a little function. Let's see if we can put a better one in there. There's the draw function. It's above the program button, and to get the draw function, you do second draw. To get a little bit better, I'm going to go to second draw, and number 6, it says draw a function. So I'm going to select 6, and all I have to do is type in the function that I want. Well, the function that I want to look at was the antiderivative of x, which was the x squared over 2. Now I'm going to let the c value be 0 here. So I'm going to look at x squared divided by 2. And what's going to happen, we're going to go back to the slope field, and it's going to draw that particular function in there. Now, it drew it sort of fast, but I think what you can see is that it, of course, widened it out a little bit. That's what happens. I mean, you learned that back in Algebra 2 when you're talking about the conic sections. But it seems to be a much better fit if you try to trace. Now, technically, you're not tracing these things. Technically, these are tangent lines to the curve. So at any particular point, all these little lines are tangent to the curve that I'm looking for. However, in actuality, you sort of follow it as a little road map wherever your point is. Now, remember our C point, we let C be 0. If I let C be 1, it should draw the same parabola but just up one step. Or if I let C be minus 3, it should draw a similar parabola but down here going through the initial condition 0, minus 3. Well, let's do that. Let's do another second draw. I'm going to select 6 again, and this time I'm going to draw x squared divided by 2 minus 3. Because, again, this constant, we don't know what this constant is. So I'm just seeing what happens if it's the minus 3. And what I should get, there's minus 3 right there. You saw the parabola come down through that different y-intercept. So what do we have here? What do we have here with a slope field or a tangent field? What we have is, in fact, the whole family of antiderivatives for that function. Depending on what constant you put in. You could have little parabolas up here. You could have the big parabolas that come down to the bottom like that and go back up. This gives you a whole family, and you can see what the graph looks like by tracing through the slope field. at some initial point. So for instance, and I'm not real sure what this point is, but let's say if that's a 3, this looks like at least a 7 or 8. If I wanted my initial condition to be 0, -8, then the parabola I would look for would be this one down here. Or if I wanted my initial condition to be 5, 0, and that was out here, then the parabola would go through that point. I would try to draw the parabola to be tangent to these little tangent segments. It would be somewhere in that area. Now, let's do one that's a little bit more complicated. That one was y equals x, or dy dx equals x. Let's do one that's a little more interesting. At least I find it so. I've just got to figure out how to put it in. It's e to the minus x squared. So I'm punching the second natural log, and that gives me e to the parentheses, and I want to put in minus x squared. Now, let's just graph that function. Let's just go back and do a simple graph of that function before we do a slope field. I want to see what that function looks like. So I'm going to choose a window. The window I want to choose, that's the standard window, I think. Let's choose from -3 to 3. And the y-min, I just happen to know 0. Let's try it about 3. I don't need any negative values there. E to the exponent is not going to give me any negative values on the y. If we just graph, we're not going to slope field this one yet. We're just going to graph it to look at it and see if it looks familiar. Well, I hope it does. Oh, okay. There's a question here with my little group. How do you get rid of the previous slope field? Did you hit second clear? Second quit? What?
I just hit clear. I hit second quit when the slope field was up.
Okay.
And then put in the window, and I've got that one.
Okay. This should look familiar. This should look at least similar to what you remember from your statistics, your probability and statistics, as the Gaussian curve or the bell curve or it's got several names for it. My understanding is the French call it the Laplacian curve, and the Germans call it the Gaussian curve, and the Americans call it the bell curve. But it's one that you at least should be familiar with the shape. It's one that we use to find area under the curve for probability and for finding out whether a particular piece of data or a set of data provides us something with statistical significance. You've seen the curve before, I'm sure. Okay, I want to now go to the program. I want to graph the slope field of the antiderivative of that. I want to find the antiderivative of that function. So I'm going to go to slope again. And I'm going to draw the slope field over the same window. I didn't change the window, so the window is still -3 to +3 on the x-axis, 0 to +3 on the y-axis. And it takes a while. It's just doing quite a bit of graphing. Now, depending on what your initial conditions are, obviously we have to choose some initial condition that's given. But let's say we want the antiderivative, the particular antiderivative. There's a whole family of them, but the particular one we want, say it goes through 0, 1. It goes through this point right here. Well, if I take this point and sort of follow the patterns of the tangent lines, it looks like I have something similar to that. Now, if I chose like 0, 2, it looks like it would be a similar shape. It just shifted up higher. So I think if you sort of follow the lines, follow the little tangent lines, you can see the curve. Now, the interesting thing about this is if you try to take the antiderivative by whatever technique of e to the minus x squared, you aren't going to find one. So this particular construction, as are a lot of constructions, is important because it shows that the antiderivative does exist. The graph defines it. We see the graph. We just can't find a particular equation for the graph. In addition, this construction is useful because the graph allows us to see the, sort of the qualitative behavior. We can see increasing, we can see decreasing, we can see curvature, we can see that there looks like there's some type of point of inflection somewhere in here where we go from curve up to curve down. Looks like it's an increasing function with some type of asymptote out here going to the negative, in the negative direction and going out in the positive direction. It looks like it sort of flattens out. If it's not asymptotic, at least it really stops increasing a lot. Maybe like the natural log function. When the natural log function really gets out on the positive, way on the positive x-axis, it really flattens out. So slope fields can help us when there are not, when there's nothing we can do to find an analytic antiderivative. Now I've heard this statistic before. I don't know how to argue it or defend it, but I've heard a statistic that says we can actually analytically compute about 10% of the antiderivatives that exist, and there are 90% that we just don't know what the equations are. Take that statistic with a grain of salt, but it's one that I've heard more than once. So that tells us that slope fields might be able to help us not only qualitatively, but actually a little bit quantitatively to find some patterns in the antiderivative. What is happening? Okay, so let's zoom out here. Let me clear that. And let's look at a particular problem associated with slope fields and using slope fields. And using slope fields to visualize this differential equation. Now, I call it a differential equation. If I have dy dx equals, let's say, y. Let's start with that one because that's one that gets a lot of use. Dy dx equals y. Now, what's actually happening is y is my equation, and when I find the antiderivative of y, whatever y is, when I find the antiderivative of y, I'm finding the antiderivative of here, I'm finding some equation for y. So I'm integrating this function on both sides so that I find out what happens. So there's a phrase I'm trying to come up with, and the phrase is not coming to my mind right now. But I'm looking at this differential equation. I want to take the antiderivative of it to solve it. Okay. We can check the general solution for this. We can check the analytic solution for this pretty easy. What does this say? This says that the derivative of y with respect to x is, in fact, itself. So that anywhere on the curve, whatever the y value is, that's the slope of the tangent line. I'm going to make a claim that says y equals c e to the x is, in fact, the analytic solution. That is the solution to this equation, an exponential. Well, if you remember when we did look at e to the x, we said e to the x was the only function that we knew of that was its own derivative, and that's what it says. Here's the derivative of a function, and it's equal to itself. But if we go over here and take the derivative of both sides, what do we get when we take the derivative of both sides over here? Now, I'm claiming that this is the antiderivative of this. If we take the derivative of this, we get dy dx. If we take the derivative of c e to the x, we get c e to the x, which is equal to y. So we can see that this is, in fact, an analytic solution, a fairly easy one to come up with, a little trick there, but nonetheless a fairly easy one to come up with. Well, let's look at the slope field of this particular differential equation. So I'm going to zoom back in. Let's go to y. Let's clear that out. Now I want to put in dy over dx. I want to put in y1 equals y. So to do that on this calculator, I'm going to have to do alpha y, and I can't find the y. Y is over the 1 key. And I'm going to enter that. Let's go to a zoom 6. And what did I hit wrong? Well, let's go to program and see what happens. Again, it's giving me the slope field. You can see lots of equations in there that are being, or lots of ways that you can trace patterns through there. Again, this was the standard. This is zoom 6, so this is minus 10 to 10. This is minus 10 to 10. This way, I think it's a 10 by 10, a 20 by 20 screen. And we've got that nice little equation. Now, what does that, slope field. Now, what does the slope field tell us? The slope field should tell us if the equation was dy dx or y prime, if dy dx is equal to y, that at any point of the y value, that should be the slope. So as you go up the y-axis, the slope should get steeper and steeper. And if we follow these things, we should get something that looks like that. Well, I hope you can remember that that does look something like the exponential curve. If we chose an initial condition down here, if we chose a point to go through down here, we would end up with some type of curve like that. If we're sticking to the positive numbers, we've got a nice curve like that. Now, to see better, or to get more detail, I'd like to go to Window and change window, let's say, minus 3 to 3. Let's go again from minus 3 to 3. Now, if I want to redo this, I'm going to have to go back to Program, go back to the slope field, and again, it's sort of a little zoom-in picture, which is exactly what it is. It's a zoom-in picture of the first one. It's a little bit clearer what's happening to the curves when you zoom in a little bit. You can see a much better pattern, a much better path to follow here. What is right here? Right here, y is 1. It looks like y is 1 right there, and we expect all the tangent lines there to be y equals 1. Well, maybe this is, well, let's see if I can trace on this. I'm not sure that this won't allow the trace button. Looks like the tangent right about there is y equals 1. So you can see that above the x-axis, where y is positive, you have positive slopes. Where you have below the x-axis, where y is negative, you have tangent lines with negative slopes. And note that on the horizontal line, where y is constant, the slopes are all constant. What we have here at y equals 0, let me get my pen over here, at y equals 0 is we have a nice horizontal line at the x-axis. Okay. And again, it's sort of, the more you do it, the better you get at it. It's sort of like, how good are you at tracing? How good are you at finding the path through this to be able to get a decent picture of what your graph looks like? Let's look at one more. The equation that I would like to look at a slope field for. It's wrong button. dy dx equals minus x over y. That's the equation I would like to look at now. To see if we can get a slope field. This one we sort of knew what was going to happen. The other ones we knew what was going to happen. We were looking for it. Let's see if we can look at this slope field and see what happens before we do anything to figure it out. So I'm going to go to y1 and put in the equation minus x over y. So let's clear that. Y equals minus x divided by y. Let's go to program. Oh, I would rather go to, well, yeah, let me check the window here. I forgot what the window, okay, minus 3 to 3, minus 3 to 3, that should be, okay, so let me go back to the program. And let me zoom in a little bit on it, make it look a little bit brighter for you. Okay, you see the slope field forming, and notice that on the y-axis, where x is 0, the slope is 0. On the y-axis, where x has a 0 value, the slope is 0. Remember, this was minus minus x over y was the equation, so that you would expect that. On the x-axis, where y is 0, the segments all look pretty much vertical. Well, what happens when y was 0? Remember, the equation was minus x over y. That tells us something about undefined, tells us something about lines with that are vertical. And at the origin, there is nothing here at the origin because you have 0 over 0, and that's undefined, so there is no line segment going through the origin. There's nothing sitting there at the origin. Well, if I chose a point just to start, like an initial condition, like maybe right about here, and I follow this thing around, it looks like it's giving me something that's not a function. It's giving me something that is, in fact, looping back on itself somehow, something circular or elliptical, I can't really tell, but I'm sort of following the little path, following the little signs along the way, and I'm coming back to where I started from. Well, that's an indication that maybe the antiderivative of minus x over y is not a nice simple function. Well, in fact, it's not. It looks like it's a circle. And if we go back to the equation of a circle, like, x squared plus y squared equals some constant squared. And I believe we've seen this before. We did anti-differentiation, we did taking the derivative. What I'm claiming is that this is the solution for that. I can find it by taking the derivative of this. Well, the derivative of this is 2x dx dx plus 2y dy dx, and of course r squared is 0. R squared is a constant, so the derivative of a constant is 0. That becomes 1. So we have dy dx equals, take this over, minus 2x over to y, which is equal to minus x over y. So there we were able to use the slope field to determine that the equation was in fact circular in nature, and by doing something that I know from previous courses, well, I knew the circle equation of a circle, certainly pre-calculus, but being able to take the, do some implicit differentiation. I think I have dy dy here. That's supposed to be dy dx. I'm sorry. We can see that what we've got does in fact match up with how we were able to read the slope field. I'd like to do one more slope field for you and let you give some thought to it. So here's an equation. Dy dx equals 2 minus y. Now I'd like to give you a minute, and I'd like you to figure out, is there anything that you can figure out, not analytically, but by using the slope field? And can you sketch the curve? This would be a question. Can you sketch the curve when you have the initial condition y equal 1, x equals 0? Okay. So let me give you a minute to work that, and I'll be entering it on mine also. Okay. Let's see if I can zoom in a little bit, get a little bit better look at the slope field. Now I changed my limits from minus 3 plus 3 to minus 5 plus 5, just to get a little bit bigger picture. But we have negative slopes coming down up here. It sort of flattens out, looks like there's some type of horizontal slope somewhere in this region, and then the slopes continue to go down to be more and more negative. Well, the initial condition I asked you to look at was y is 0, x is 1. So if y is 0, x is 1, we've got a point that's somewhere right about here. If x is 1 and y is 0, we've got some point right about here. Did I say? I thought y is 1, x is 0. I'm sorry. Y is 1, x is 0. You're right, I did. Thank you. So it looks like we've got some type of curve that looks like this, if we're going to go to the point right about here. Remember, I changed mine to be a 5. If that's 5, that's about a 1 right there. And I'm doing some kind of a curve like that. Let's do it a little bit differently. I want to zoom out just a little bit more on this thing. I want to go back to the standard zoom to get a little bit bigger picture, if you don't mind. So I'm going to go back to zoom 6, which is the standard zoom. And now I've got to rerun the program. It's a little awkward, but It certainly beats computing one by hand. And we should see the same thing. We should see the same tangents coming down with negative slopes. Right about in here, it should sort of come to a little horizontal line. And then the slope should become positive, steeper and steeper as it goes down. So a second, now let's ask that same this question I did ask incorrectly a while ago. Let's look at what happens when x is 1 and y is 0. If x is 1 and y is 0, we're right about here. We've got a graph that looks like that. It falls off very steeply here. It quickly comes to some type of an asymptote, or at least it looks like it's some type of an asymptote right here. If we looked at maybe when y was 3 and x is 0. So if we look at the ordered pair maybe 0, 3 to find the initial condition, and that's the equation we're looking for, maybe through this point right about here, that looks like about 0, 3, then the graph is going to look like that. It's going to come down very steeply. It's going to go through this point, and then it's going to come out again. It looks like it's some horizontal tangent out here. So, what are slope fields? Now, that still doesn't give us the equation. To find the equation, we're still going to have to go back, and if we're lucky, we can find it analytically. But remember, there are a lot of equations that you cannot find the antiderivative of analytically, but you can still see some, I think, some very good qualitative behavior of the function if you're able to identify an initial condition. So, that is, I've lost my button here, hang on. There we go. That's a look at slope fields. I'm not real sure slope fields are reasonable to do in a short period of time if you do not have some type of technology to generate them, whether you have a calculator or whether you have access to Mathematica or Maple, one of the computer algebra systems. I've had a little bit of experience with Maple. I taught a couple of courses using Maple, and it's really nice. It really is nice. It takes a lot of that drudgery away so that you can talk about the nice things. What I want to do now then is move back to the traditional analytical part here and start talking about antiderivatives. How do you find antiderivatives? What are the techniques for finding antiderivatives? And we looked at a few of them last class. Do a quick review on a couple of those. And the first one, of course, is just regular polynomial functions. Suppose you have x to the n power and you want to find the antiderivative. You want to do the little calculus magic to a nice little polynomial term, x to the n. Well, you remember it's x to the n plus 1. You add 1 to the exponent and then divide by the new exponent. So the integral, say, of x cubed with respect to x is going to be x to the 4th over 4. Now, if this is an integral without limits so that we can evaluate it, remember it's a whole family of functions that might shift up or down that we certainly saw when we were looking at the slope fields. There's a whole family of functions, and I think that's one of the things that slope fields are good for emphasizing, is that you don't, if you have a general antiderivative, you've got a whole family of functions that might be the answer. You need some initial condition to tell you which one you're looking for. Okay. Another way of finding antiderivatives that we've talked about, although indirectly, is something like, if I know the derivative of the tangent of x dx is secant squared x, Well, if it's the antiderivative, if I've got a handful of these things, in particular the trig functions, some of the trig functions, if I've got those memorized, then I ought to know the antiderivative of not necessarily the tangent function, but I certainly ought to know the antiderivative of the secant squared. So if I'm asked for that, then I should know that, again, plus a constant. So general polynomials, pretty easy. Some that we already have memorized, pretty easy. Another one that we already have memorized should be e to the x. If the derivative of e to the x is e to the x, then the integral of e to the x is e to the x. And you're going to see me hesitate and come back and put the plus c probably half a dozen times. And so those aren't anything new or challenging or working a problem. As a matter of fact, when we do these, my students generally ask, well, when are we going to do a problem that we can actually work? Well, there is a technique, and the technique is called U substitution, and U substitution is a nice technique, not for every function, but it's certainly good for a lot of functions. And let me see where we've got it right here. For that general derivative, let's look at the derivative. Let's go back and look at the derivative of something like x squared plus 1 all squared dx. Now, this is what we talked about earlier when we were taking derivatives. I'm going back and talking about derivatives so that we can go back talking about antiderivatives. What was the little thing that we used here that was a little extra piece we had to add on? Well, it's a composite function. It's a function to a function, or function in an x squared function. We used the chain rule. So whereas the chain rule took care of composite functions when we took the derivative, U substitution is going to be the reverse. What we're going to do with U substitution is going to take care of the chain rule when we work backwards. If I take a derivative and this little extra thing pops out, remember the derivative of this should be 2 x squared plus 1 to the 1 power, then I have to stick on this little 2x because that's the derivative of x squared plus 1. The chain rule is something that's going to be able to absorb a little term like this. U substitution is something that's going to be able to absorb a little term like this and move backwards. So in general, the form for U substitution is the integral of some possibly composite function u to the n du is going to be equal to u to the n plus 1 over n plus 1 plus the constant. Of course, there is one little caveat here, and that's where the natural log comes in. N cannot be a negative 1. So n cannot be a negative 1. So if u is a composite function, I need u to the n, and then I need the derivative of the composite function here. So that's not a simple dx, where dx is just a plain old dx. This is a du, which might be the derivative, well, will be the derivative of whatever the u function is, and the u function might be some type of function made by composition. So let's look at a little example here. Pretty simple, where du happens to be real easy. Now, if I'm going to work this the polynomial way, where it's term at a time, what I'm going to have to do with this x plus 2 is to write it down 5 times and multiply, or try to remember my Pascal's triangle from all my coefficients and exponents, or maybe if I'm lucky enough to have a TI-92 or a TI-89, I can just slide it in there and get a nice expanded answer. But if I'm working it by hand, I certainly don't want to have to expand that x plus 2 to the 5th power. So what I'm going to do is use substitution, and I'm going to choose something to be the u function. Well, the obvious thing to choose here, since it's the only thing here, is I'm going to let u be the x plus 2. Now, if I have u, I also need du. Now, in this particular case, du is real easy to come across. Du is just the derivative of u, and the derivative of x plus 2 is 1. So du is 1 dx. So what I've got from this is an ability to substitute. X plus 2 is going to become u. Dx is going to become du. And I can rewrite this as the integral of u to the 5th du. Now, instead of all this nasty stuff up here, look how much it's been simplified. And that's the whole point of u substitution. You've got something that's nasty, you've got something that's all mixed up, you want to turn it into a nice little polynomial type function that you can take the antiderivative of. Well, what is the antiderivative of that? Well, that would be u to the 6th over 6 plus your constant. Now, we're not quite through with this because we're not taking the derivative. The original problem was not in terms of u. We're using u. We translated it into u so that we could easily manipulate the problem. Now we've got to translate it back into the x. So I'm going to try to write it down here on the bottom. The final answer, I'm just taking out the u and putting in x plus 2. X plus 2 over 6, to the 6 over 6 plus a constant. Now, again, this u substitution that we did right here was a fairly simple one, mostly because the derivative of u was, in fact, just 1 dx. They can get a little more complicated, and when they get a little more complicated, we have to sometimes do something to manipulate the function, and there are only a few things we can do to manipulate the function to find the appropriate value of du and u. So, another one. Let's find the integral, the antiderivative, of the square root of 4x minus 1 dx. Now, what I do, and I think most of my students do, mostly because I model it, not because it's something that's necessary. Anytime I have a square root, I tend to write it with an exponent of 1/2 because it puts it in the form that's just easier for me to identify that I add 1 to the exponent and divide by the new exponent. So I'm going to rewrite that as 4x minus 1 to the 1/2 power, quantity to the 1/2 power, dx. And again, I don't have much choice here to substitute, so I'm going to let u be 4x minus 1. Now, in general, what you're looking for, how do you know what to substitute for the u? Well, in general, what you're looking for is something that is a function and something that is its derivative, and we'll see some stuff that's just a little bit more complicated in a minute. But right here, I'm going to let u be 4x minus 1. So in that case, du, now the derivative of this is 4 dx. So if I go back and look at my function, I can see that I can replace that with a u, because this will be u, 4x minus 1 is u, that'll be u to the 1/2, but I don't have a 4 dx. I just have a dx here. But I can add in, or I guess multiply in a factor of 4, but I just can't increase the value 4 times without compensating. So I'm going to multiply it by a 1/4. And that 1/4 times that 4 makes a 1, and I don't have any change in my value. Now, one of the things that we talked about last week is if you have a constant, you can take the constant on the outside of the sign of the integral sign. So I'm going to rewrite this as 1/4 times the integral of 4x minus 1 to the 1/2 4 dx, where I can see this is the value that I'm going to substitute in for u, and this is what I'm going to substitute for du. And I've got this 1/4 sitting out here that I can't get rid of. It's part of the problem now. So I have 1/4 times the integral. This is u to the 1/2, and this becomes du. And again, that's what we said a while ago. The whole purpose of u substitution is to turn it from something nasty that we can't do it into another form, to translate it into something that we can handle. Well, the antiderivative of u to the 1/2 is u to the 3/2 over 3/2. I'm going to multiply that by the 1/4, and that's going to be plus a constant. Now, the 2 cancels with the 4 and leaves the 2, so you have a 6 in the denominator, and your solution, you could either do u to the 2/3 over 6 or 1/6 u to the 3/2, plus the constant. Now, we've got one more step to perform. Remember, the original problem was not in terms of u, the original problem was in terms of x. So I want to go back to where I chose what my u was, and I'm going to go back to my final answer, take out the u, and resubstitute back in the 4x minus 1. So that's going to be 1/6 4x minus 1 to the 3/2 plus a constant. Let's look at one or two with some simple trigonometric integrands in them. Let's do a little bit of review on the cosine one. We know the derivative of the sine of x dx is the cosine of x. So we would expect the integral of the cosine of x dx to be the sine of x plus a constant. So if we review that, and that's one of those that we that was one of the ones we listed earlier that we just sort of know because we know the derivative, then let's look at something a little bit more complicated with the cosine. Let's look at the integral of the cosine of 7x plus 5 dx. Now, this is again a composite function. Remember, for composite functions, to take the derivative, we employed the chain rule. The reverse of the chain rule is u substitution. Now, in this particular case, the cosine is not the one I've got to worry about simplifying. The one I've got to worry about simplifying is the 7x plus 5. So I'm going to select u equals 7x plus 5. Then du is going to be 7 dx. The derivative of the u function, what we let u be, is 7x plus 5, so the derivative is 7 dx. Then we can see a little bit of quick substitution. This was going to become the cosine of u, but I don't have enough for the du. So I'm going to go ahead and add a factor of 7 right here. But if I add a factor of 7 here, I've got to compensate for it by multiplying by 1/7. So what's going to happen? I've got 1/7 times the integral of the cosine. Now this is u, and this is du. And of course, we just saw the integral of the cosine of u du was the sine of u. So that's 1/7 times the sine of u plus a constant. Now, again, u. We substituted to find the u. We got out of x into u. Now we're going back to x. So it's going to be 1/7 times the sine of 7x plus 5 plus the constant. Okay. Let's see if we can do this one. This one's going to be a little bit of a challenge. If you remember your trig substitution, if you remember your trigonometry, let's find a form for the integral of 1 over the cosine squared 2x dx. Now, I'm going to let you look at this one for a second. 1 over the cosine squared of 2x dx. I'm going to let you look at that one for a second, remembering that 1 over the cosine squared has a different form if you go back and remember your trig. Maybe I'll have to write that just a little bit better. 1 over cosine squared 2x dx. That might make it look a little bit better. I've got it shifted down a little bit. It looks sort of like a subscript. Let me let you think about that one for about 10 or 15 seconds before we see what's going to happen to it. A couple of hints. One, I see where my u is going to be substituted. And I also know something about the reciprocal of the cosine. Well, the first thing I hope you noticed is that the secant of 2x in general is going to be 1 over the cosine of 2x. Now, I'm not substituting here. Well, I guess I am substituting, but I'm not substituting for the integration. I'm just substituting to get a better form. If 1 over the cosine of a function is the secant of the function, then 1 over the cosine squared should be the secant squared of the function. So the first thing I'm going to do, and this is not u substitution part yet, this is just changing this to something I can take the antiderivative of. That's the integral of the secant squared of 2x dx. Now, the reason I wanted to change it to that, we looked at it a little bit earlier. I think that was one of the ones I put up on the screen. We should know the integral of the secant squared because the secant squared is the derivative of something. The secant squared is the derivative of the tangent. So now I'm able to do some u substitution. Let's let u equal 2x, and we'll have secant squared of u. But then if I'm going to integrate in terms of u, I need a du. And of course, it's easy to see here that du is 2 dx. So let's see, what do I have over here that I can substitute for, and what's missing? Well, u is 2x, so that 2x right there, that's the u. I'm going to take that out and put a u in there. But I need a 2 dx. I've only got 1 dx, so I'm going to put in a factor of 2. But if I put in a factor of 2, I've got to compensate for that by putting in a factor of 1/2, so that I don't change the value of the integrand. Now, should fall off pretty easy here. The integral of 1/2 of secant squared u, that part right there becomes du. And of course, the integral of the secant squared is the tangent of u. So this becomes 1/2 the tangent of u. Again, since it's an indefinite integral, plus a constant. And then substituting, remember u is in fact 2x, 1/2 the tangent of 2x plus a constant. We resubstitute back. It's sort of like, a student made this analogy one time. I'm not sure I've worked through the analogy, but it says it's like you're translating something and you're working something in a French class, you don't understand it, you translate it to English so you can figure out what they're saying, and then to answer the teacher, you have to turn it back into French. So I'm not sure that analogy holds 100%, but at least it worked for that student. One that's a little bit more complicated looking, although I'm not real sure it's more complicated, is one like this one. Again, we're working with U substitution. So I've got a polynomial, x squared plus 2x minus 3, all squared, x plus 1, dx. And this is sort of the standard, form, or the standard concept that I have when I think of U substitution, that up here I've got two different functions that I'm multiplying. I've got a product of two functions. I've got some f function and some g function that I'm multiplying. And if I look at those two functions, I see that one function at least has the skeleton of the derivative of the other function. And when I see that, that's when my little click goes off in my mind that says I've probably got something here that is of U substitution form, something that I can substitute U in there. So I'm looking at these two functions. I've got a function f times a function g. And if this one happens to be somehow or another closely related, at least through a constant, you can multiply through by a constant, to the derivative of this one. Well, look at the derivative of this one. On our heads, we can say 2x plus 2. And that looks like that's the constant here has a derivative of 0. So the derivative here is 2x plus 2. That's x plus 1. If I double it, I get 2x plus 2. So this is the skeleton, at least. It's got the variables and the basic polynomial, a factor of the derivative of this. Then it should be a good candidate to try U substitution with. So let's do a little quick U substitution here. I'm going to choose the more complicated one, the one that is not the derivative of the other, and let U be x squared plus 2x minus 3. In that case, du is 2x plus 2 dx. Now when I go back for U substitution, this is U squared, which is very nice. I almost have all of du right here. The only thing I'm missing for du is a factor of 2. I can factor that 2 out there, and I can see I've got the x plus 1, I've got the dx, but what I don't have is a factor of 2. So if I add a factor of 2 in there for this to become the du, I've got to compensate by putting a 1/2 out in front of the integral sign, so that the 1/2 times 2 is 1. Now, you substitute, it falls off pretty quickly. 1/2 the integral. This is my u, so that becomes u squared. And 2x plus 1 dx, 2x plus 1 dx becomes my du. We can take the antiderivative of that quite easily. U cubed over 3. Multiply that by 1/2. Plus the constant. That's equal to 1/6 U cubed plus the constant. And of course, we're going to do our translation back into French. 1/6 U cubed plus the constant, where U was x squared plus 2x minus 3. Now, U substitution does not work for every type of problem. There are many types of problems that U substitution does not work for. So you have to sort of have this nice little feature up here where you have the product of two functions are built in somehow. You've got to have one function and a second function as a product, and somehow or another you multiply, when you multiply them together, before you multiply them together, you can see that one is somewhat the derivative of the other, at least by a constant. It could be missing a constant. It can't be missing an x now. If this were an x cubed, and I took the derivative of this, that would be 3x squared, and this was not an x squared. I couldn't multiply through by x because I need to keep my x's in my integrand. The only thing I can play with here, the only thing I can factor out like this, is a constant. So don't stick an extra x value in there. Don't stick another variable in there. The only thing you can play with like this, the only thing that little manipulation will work with is constants. Let me give you one with some trig, some simple sine and cosine. Let's look at this is sort of a precursor of things to come, but let's look at sine to the fourth of x times the cosine of x dx. Now again, that's a composite function, so I'm going to let you choose a substitution and let you take a look at that one for a minute. Oops. You can see I was already taking the antiderivative in my head before I did my substitution. Sorry about that. Okay, if we let u be the whole sine function, the sine of x, then that becomes u to the fourth power. And then you can see that the cosine of x dx is the whole du, because the derivative of the sine is the cosine. Well, this is very easy to take the antiderivative of x to the fifth over 5 plus a constant, u, okay, u to the fifth over 5 plus a constant. And then to substitute back, we're going to take the u out and put in the sine, so it'd be sine to the fifth of x over 5 plus a constant. So, one other little comment, I'm going to give you two problems to look at for just a second here. One little comment, I want to try to remember this. Do you remember the integral of 1 over t? And of course the variable doesn't matter, 1 over t, 1 over x, whatever. It's sort of a dummy variable anyway. 1 over t dt. Now that was one that we mentioned a little bit earlier. If I rewrite that in my exponential form, I get t to the minus 1 dt. And when I try to treat this like a polynomial, I add 1 to the exponent and get a 0, and then I divide by the new exponent, which is dividing by 0. And we know we can't do that. So do you remember what the antiderivative of 1 over t is, I hope? It is, in fact, that is true. I shouldn't have scratched that out. It's the natural log of t plus, of course, since it's a, oops. I would have remembered that as soon as I tried to work with a negative number. It's an absolute value because, remember, the log function only works for values greater than 0. Now, I'm getting ready to give you a couple of problems to look at right now. You're getting ready to use this one, and you're going to go back and look at this relationship here between the sine and the cosine. So let me write these two down for you and give you a minute, a little bit of practice here. The first one, the integral in the numerator, I'm going to say x plus 2 dx x plus 2 quantity, times dx, and in the denominator, I'm going to say x squared plus 4x plus 7. Let's see if we can work both of these on the same sheet of paper. The second one I'm going to ask you to look at is e to the sine x times cosine x dx. Now, between you and me and no one else, those look pretty complicated to me. And the whole purpose of u substitution is to take something that's really nasty, looking like that, and turn it into something that is easy to take the antiderivative of. So I'm going to give you about a minute, minute and a half or so to work on those couple of problems. As soon as we get through with it, I'm going to try to do two. Yeah. As soon as we work these two, I'm going to, or at least set them up for working. We're going to take the break. Yes. So this one, you've got 1/2 the integral of 1 over u du. Okay, because the u is in the denominator, so it's 1 over u, and the numerator is du. Now, what did we say was the antiderivative of 1 over u du is the natural log of u, so we should have 1/2 the natural log of the absolute value of u plus a constant, which is 1/2 the natural log of x squared plus 4x plus 7 plus a constant. Okay. Let me set this one up, and then we'll take a break, and we'll come back in about 15 minutes and finish working this one. U is going to be the sine of x. That means du is going to be the cosine of x dx. The derivative of the sine is the cosine. If we do that, you see that we have the sine x here, so it'll be e to the u du. So the function now looks like e to the u du. Now, we mentioned that a little bit earlier. The integral of e to the u du is e to the u plus a constant. And u is, of course, well, I said we were going to work it when we get back. I think we just worked it. Is e to the sine x plus a constant. So, it's time to take about a 15-minute break. Give you a chance to go back and see see if that program at the beginning, maybe, if you've got this on tape, a chance to go back and see if that calculator program at the beginning, if you can see it and you can pause well enough to see it. And we'll be back in about 15 minutes. Back, we spent the first part of class today looking at a little review of what the course was about. Some talked a little bit about the influence that the new calculus, the reform calculus movement has put on calculus, and we've seen a little bit of it in the class, in particular the technology. What we want to do now is continue on with techniques of integration, although I do have one particular problem for you. I think it's a clever problem, and I'd like you to sort of struggle with it yourself. It's certainly not a homework problem that has to be turned in, but it's a problem that is clever and it's interesting, and it makes a nice connection for the fundamental theorem of calculus. If you look at this integral, it's the integral of the cosine squared 2 theta cotangent 2 theta d theta, where theta is now your variable instead of x. Again, it's a dummy variable. You could change the 2x, dx, or whatever variable you want if you don't like the theta. And the question here is, where do you choose the u for the substitution? Do you let the u be the cotangent of 2 theta, or do you let u be the cosecant of 2 theta? Well, as it turns out on this one, it'll work either way, and that's what I would like you to sort of take off after this class when you're doing some of your little activities, reviewing the class. I'd like you to see if you could work this one out. If you let u be the cotangent of 2 theta, now I certainly don't think you remember the derivatives from earlier off the top of your head, but you remember the cotangent and the cosecant appear in each other's derivatives. If we let u be the cotangent of 2 theta, then du is going to be minus 2 cosecant squared 2 theta d theta. And that's pretty convenient, because there's your cosecant squared right there if you let u be the cotangent. But if you let u be the cosecant, then the du will be minus the cosecant of 2 theta, cotangent of 2 theta, d theta. I'm writing that a little small. Let me write that a little bit larger. Minus cosecant 2 theta, cotangent 2 theta, d theta. So you can see that you're going to have to add a little negative on the inside to get a -1, but if you add the negative on the inside or on the right of the integral sign, you can compensate by putting a negative on the outside, so a negative times a negative will be a positive. Now, if you work the problems these two ways, I'll go ahead and give you the answers. I'd like you to go through the process. Let me give you the solutions, and the solutions are actually going to be the antiderivative is going to look different. Let's see. If you work it the first way, you're going to end up with minus the cotangent squared 2 theta over 4 plus c. Okay. If you work it the second way with the second u substitution, you're going to end up with a minus cosecant squared 2 theta over 4 plus c. Now, for those of you that teach pre-calculus or any course with a trig with an identity component, you remember one of the Pythagorean identities, I hope. 1 plus cotangent squared equals cosecant squared. As it turns out, if you do a substitution for that cosecant cotangent Pythagorean identity, what you'll find out is that these two are not the same, but they differ by a constant. And that's all the fundamental theorem of calculus That's all it promises us. Remember, when we take an antiderivative, we get an antiderivative in the constant, so that 1 gets subsumed in that constant. So I guess if I'm going to relate these two, I should really call this a constant 1 and a constant 2. And that constant 1 and constant 2 should differ by 1. So I think it's a neat little problem. You can choose either one of these for your U substitution. So this would be method A of working it. This would be method B of working it. You'll get this answer for method A. You'll get this method answer for method B. And they look different, but if you use that Pythagorean Pythagorean identity, 1 plus cotangent squared equals cosecant squared, then you can see that these two are, in fact, the same, except they differ by a constant. So it's a nice problem to spend a nice little chilly Saturday afternoon, or a warm Saturday afternoon, by the fireplace or by the refrigerator. The next type of system for taking antiderivatives that we're going to look at is integration by parts. Which tells me I'm going to take an integrand and I'm going to divide it up into different parts. Again, the first way we looked at integrating was, do we have a derivative? Do we have a function and we know it's derivative? We can turn around. The derivative integrated is the original function, like we've used it a couple of times, the tangent and the secant squared. The derivative of the tangent is the secant squared, so the integral of the secant squared is the tangent. We've done that with e to the x and several of the other functions, trig functions. And then we've also looked at the polynomial x to the n. The integral of that becomes x to the n plus 1 over n plus 1. The third thing we looked at was u substitution. We just got through with that. And this is a fourth major technique for integrating a function. Now, to sort of derive the algorithm that we're going to use, this is basically the product rule, where u substitution was an analogy to the chain rule. Integration by parts is going to be analogous to the, or at least derived from the product rule. If I have two functions, u and v, if I have two functions, u and v, and I want to take the derivative of them. So I want to take the derivative of the product, uv, with respect to x. Now, u is some function of x, v is some function of x. That's, remember the product rule, first times the derivative of the second, plus the second times the derivative of the first. That becomes u, and I'm going to write it as dv dx plus the second v times the derivative of the first. Now, some people, let me do this. Some people, instead of the dv dx, du dx, this is my own preference here. Some people will do this. And instead of doing dv dx, they'll do v prime. And instead of doing du dx, they'll do u prime. And there's absolutely nothing wrong with that. That's just a different notation. The problem I have with that is once I start doing this little prime stuff, I get real sloppy. And once I get sloppy, my v's and my u's tend to merge together if I don't pay attention to my dv and my du. So I prefer this with the dv dx, du dx, rather than the primes. But if you would rather write it like that, you certainly may. There's nothing wrong with it. Okay. So in the differential form, this becomes, if we just sort of remove the dx, we get d of uv is equal to u dv plus v du. Now I'm going to flip some stuff around here. The v du I want to take over to this side, It'll make it a minus v du. So I'll have d of uv minus v du is equal to u dv. And now I also happen to be teaching college prep geometry, and my question was, how can I flip these two sides so that I can have u dv equals d uv minus v du, and they'll say the transitive, the distributive, the associative, they'll give me all the properties, and finally somebody will say the symmetric property of equality. Okay. Now, I've just done some manipulation. I did the product rule up here, and I just did a little bit of a manipulation to get this stuff down here. Now, when I get that, all I have to do now is take the integral of both sides. What I do to one side of the equation, I do to the other. So I take the integral here. Now, this is the difference, so I can take the integral here and the integral here. If I do that, I'll get the integral of u dv equals the integral of the derivative of uv minus the integral of v du. And, of course, the integral of the derivative equals uv minus the integral of v du. And that is the formula that we're going to use for integration by parts. What we've got is what we're going to be presented with are two different functions. One function we're going to choose to be the function u. The second function we're going to choose to be the derivative of some other function that we can identify. Now remember, back on integration by parts, not integration by parts, back on u substitution, when I had the two functions, I had one that was a function and the other that looked like g was the derivative of f. Well, in this case, this is the derivative of not u. This is going to be the derivative of some other function out there. So if this dv happens to be the derivative of u, you probably can go back and look at u substitution, which is a little bit easier. So again, we're looking at the product of two functions. I've got this function times this function, and I'm going to identify it, do some substitution, do some identification. I'm going to identify one as a u, identify one as a v function, and then just use this particular formula to solve it. So as we are working these, I would like you to take this little function and sort of set it, that little formula, and set it over to the side, because we're going to be referring to this quite a bit as we work a few problems. Well, let's look at one. Let's look at the integral of x times the cosine x dx. Now, as I look at x times the cosine x of dx, I say to myself, gee, I can't do a u substitution because the derivative of the cosine is the sine. I can't stick a sine in there somewhere. And if I take the derivative, I let x be u, the derivative is 1, and then I'm stuck with an extra cosine in there. So there's no way that I can do the u substitution on this one because these two functions that are being multiplied together just aren't compatible, at least for u substitution. But what I can do is my integration by parts. And this is what I want to do. I want to choose one of these two functions to be the u function, and I want to choose the other one to be the dv function. Now, sometimes it's hard to tell which one should be which. So for the first couple, I'll just go ahead and tell you what I was told to do is do it one way. If it worked, that's fine. If it didn't work, I did it the wrong way and go back and do it the first way. But I'll go ahead and tell you what we're going to substitute here just to see the problem work. I'm going to select u to be the x. That means I'm going to select the dv. Well, it's not selecting. It's the only option left to be the cosine x dx. So I'm going to let u be the dv. I'm going to let u be the x part of the function, and I'm going to let the dv be the other part of the function, the cosine x dx. Now, if you look back at the formula that I said we needed to keep, I need to find u. Well, I've got u selected right there. I need to find a v. Well, I don't have a v, I have a dv, so I've got to take the antiderivative of that to find the v. I've got dv selected from here, so v is going to be, obviously, it's going to be the sine of x. Now, what else do I need? I have the u now, I have the v, minus the integral. I've got the v. What I don't have is the du. But I do have u. Since I have the u function, I can find the du, and the du is going to be 1 dx. So, what I've done is I chose one of my two, I've got a product of two functions here. I chose one of my functions to be a u function, the other one to be the dv. I took the antiderivative of dv to get v, I took the derivative of u to get du. Now that I've got this information, all I have to do is substitute it into the formula. Again, the formula is the integral of u dv, and that's what I'm looking for. I chose this to be u, this to be dv, this is what I'm looking for, is equal to uv minus the integral of v du. Well, this is what I'm looking for, so all I have to do is substitute over here. To substitute in the u, I've got x. To substitute in the v, remember v is the sine of x, minus the integral. Now, this is still going to be an integral part, and what's it going to be the integral of? It's going to be integral of sine x, because that's the v part, and du is just dx. So that's the integral of sine x, 1 dx. Excuse me. Now, the first part here is clean. I mean, I've taken out the integral sign. I don't have that's clean. That's part of the answer. This is not quite as clean as it should be, because I can still take the antiderivative of the sine of x. But I ought to be able to do that quite easily, because the antiderivative of the sine of x is the cosine of x. So this is just equal to x sine x. Remember this part, I don't have to do anything to it once I get the uv, minus, I'm taking the integral here, I can do that in my head. The antiderivative of the sine x is the, positive. I'm sorry, thank you. The antiderivative of the sine of x is the negative cosine of x. Since it's already a negative is a positive. Thank you. I meant that to be the plus c, not the dx. So, let's, I'm not trying to beat a dead horse here, but let's talk about what we did one more time to see the little steps here. The first step was when I looked at my function. I have two functions up here. When I look at my integrand, I have two functions that I'm multiplying. It's a product. I choose one of them to be u and one of them to be dv, not v, but dv, because remember my formula says I'm starting with u dv. So I choose one to be u, one to be dv. Once we've chosen that, I take my dv, I take its antiderivative to find v. I take my u, I take its derivative to find du. So now I've got four pieces of information. I've got a u function and its derivative. I've got a v function and its derivative. Then with this information, all I do is substitute into the formula. I've got u, I've got v, I've got v again, that's nice, and I've got du. Everything gets used somewhere in here, in the formula. Then this just drops, this is just clean. This comes down, whatever u times v is fine. What I hope happens here is that the integral that we get left is much more simple than the integral we started with. If this thing is still nasty, then maybe what has happened is if it can be done by parts, that maybe I should switch these two around and let this one be u and this one be dv. Because what I hope happens is this integral is going to be a heck of a lot easier to take the antiderivative of than the initial integral. Now, we're going to see some in a minute where we can still take the integral of this, and it's not real clean, but it's still quite doable. It's easy enough to do. But that's the goal. The goal is to do this UDV selection so that when you get this integral's pretty easy to take. What you don't know at the beginning is if that integral is going to be easy. Like I said, if I go through here and I go through this, and this is something like tangent cubed of the square root of 5 over 72 pi r squared x, then I'm probably going to say, this is not the one I want to take the antiderivative of, and I'll go back and rework the problem by choosing u and v separately. Let's look at a few more integration by parts to get the formula down. Again, to get the form down, again, you need to keep that particular formula right beside your notes as you're writing so that you can keep referring to it. Okay. Excuse me. Okay, let's look at the integral of x times e to the minus x dx. And again, that's not any of the forms that I know how to do so far. It's certainly not integration by u substitution, because the integral of e to the u is e to the u, and I've got an x hanging out there. So what I'm going to want to do here is the same thing I did a while ago. I want to choose one function to be a u and one function to be the dv. Again, I'm going to let u be the x function, which means dv is e to the minus x. Now, one thing that you should pay attention to when you're choosing your dv is that your dv, you should be able to take the antiderivative of it fairly easy. If this was something that I couldn't take the antiderivative of quite easily, I probably wouldn't select that to be my dv. Now, once I have u, I need du. And of course, du there, that's e to the minus x dx. E to the minus x dx is part of the derivative there. Du is just going to be the derivative of x is 1 dx. You don't have to write the 1. It's certainly okay if you do. And we've got to do a little integration here. E to the minus x is the antiderivative of this e to the minus x. That's just it looks like that form. If I go backwards to check, which is something that I always encourage students to do, go backwards. If I'm going from here to here, I want to go backwards to make sure that the answer works both ways. If I take the integral of this is a quick u substitution here, a chain rule, e to the minus x, but times the derivative of this would be minus. So I would expect that to be minus, so to get rid of that minus, I'm going to have to put the minus there. Okay. Now when I go e to the minus x, the derivative is going to be e to the minus x times the derivative of the exponent, which is minus 1, and it'll make that minus into a plus, which is what I have down here. So I've got a nice u and a nice v, and I'm ready to write down the formula and substitute into the formula. So again, I'm going to write the integral of u dv equals the u v minus the integral of v du. And now we're substituting. U is x, v is minus e to the minus x, so u is x, v is minus e to the minus x, minus, again, this is minus e to the minus x times dx. Now, we can clean that up a little bit. This minus will come out here and make this a plus. I'm not sure I need to do that, but and I've got my plus c on here that I'm going to add in a minute. I haven't gotten that far out yet. So I don't have to do anything with this. This is just a regular good old function. I don't have any integrals or anything, but I've got to take the integral of the e to the minus x, and of course the e to the minus x, I think we just did something like that, should be a minus e to the minus x. So this becomes minus x e to the minus x plus a minus e to the minus x, or minus x e to the minus x minus e to the minus x. And of course, I'd like to wait till the very end to add my constant. This is very much algorithmic. It's very much an algorithm. There's not a lot of thinking that you do. There's not a lot of creativity that goes on here. There's a lot of thinking. It's not a lot of creativity that goes on here. The key is, are you able to select the right one for u and the right one for x? Excuse me, the right one for u and the right one for dv. There is a little mnemonic device that sort of tells you which types of functions to choose for what. And I've heard several people say that it works most of the time, and I've heard other people say that they don't know if it works all the time or not, but they've never found a time when it didn't work. So I'd like to give you that little mnemonic device to tell you which one to choose for you when you do integration by parts. And the mnemonic device is ILATE. To choose, then, this is what you're selecting to be the u. The first thing you want to go for is I, which stands for inverse trigonometric functions. Now, we're not going to do any of those, so don't panic. But if you do happen to do some with inverse trig functions, that's the first one you want to go for. And then you let the other part be the dv. L stands for the log functions. So if you have any log functions, if you don't have inverse trig function, you do have log functions. That's what you would choose. A stands for algebraic functions. T, I bet you know that one, trig functions. And then E, well, the only one left, we just used these, exponential functions. Okay. So, I'm not going to guarantee that if you follow this little mnemonic device, it's going to work every time. But like I say, I've talked to a lot of people, and a lot of people say they're not sure it works every time, but they've never found a time when it didn't work. The two we just did, notice algebraic comes before trig. So on this first one we did, we had an algebraic and a trig. We let the algebra be u, the trig be the dv. So it certainly worked there. And what was the one? I can't find the one. There it is. The one with the e to the x we just did. Algebraic comes before exponential. And of course, we let the u be the algebraic expression, and then we let the other one, the exponential function, be the dv. So at least in those two examples, that selection worked. And I think you'll find out that if you can sort of keep that little ILATE word written down in the margin of your book while you're working problems, it'll help you choose the correct value for the u and the v. Now, that still doesn't mean if you choose it, it doesn't mean that every problem that you can solve, every function that's a product of every, let me slow down and say that again, that every integrand that is a product of two functions is going to be integrable by this method. But if it is integral by this method, that's the way that you want to do it. Okay. Let's keep doing a few more problems here. and let me get organized. Remember when we did when we looked at the function, we said the integral of u dv is equal to uv minus the integral of v du. And what we said was, what we hoped is when we chose this thing, that this part right here becomes easily integrable so that I don't have to do a lot of work on it, and then I can let this nasty integral that I couldn't do just straightforward, I can divide it up into this part and this part, and this part's easy to do, so I've made a hard problem easier. Well, what I want to do is look at one where this one doesn't get any harder, but this one doesn't particularly get any easier. And it's a neat little technique. Sometimes you have to do things more than once. You have to do by parts more than once. So let's look at this particular equation. This is fairly standard example for this variation of the technique, I guess, would be a good thing. And let me ask, what are you going to choose here for your u, and what are you going to choose for your v? Well, let's do that. Okay. If I know u, what is du? E to the x, dx. And what is v? Well, the derivative of the something is the cosine. The derivative of the sine is the cosine. Okay. So now we're ready to choose this, substitute it into this method. The integral of u dv, into this method, into this formula, is u v and I'm going to subtract v du, which is e to the x sine x dx. Now look at that particular integrand. It's amazingly similar to the one originally that we worked at the first of the problem, or the problem we're working. It's just e to the x matches, sine x matches with cosine x. I can see that this also might be something that is integrable by parts, where I can do the same thing I did up here. Instead of e to the x and cosine x, do it for e to the x and sine x, because this, otherwise that's not, at least to me, that's not readily integrable. So I want to take this little piece right here. Now I'm going to get another piece of paper, and I'm just going to write this little piece right here. E to the x sine x dx. And I want to work on that one. When I figure this one out, if I can figure this one out, then I want to come back and substitute it in here, and then we'll continue working this problem. But it looks like I'm going to have to do something sort of special to that one. So let's do this one. This second by parts. Let's do the same thing we did. This time dv is sine x dx. V will be, careful now, minus cosine x. And du will be, of course, e to the x dx. So now I'm working this as its own problem, and let me write the formula down. The integral of u dv is equal to uv minus the integral of v du. That's equal to uv, which is minus e to the x cosine x, minus the integral. Now v du is minus e to the x cosine x. So it's another minus, so I'm going to make it a plus. So another minus in here because of this cosine. So I'm going to take it out here and make it a plus. E to the x cosine x dx. Now look what happened when I took the e to the x cosine x and did it by parts. I got e to the x, it's with the cosine x on this part at least. I got this part out here, but this part in here switched back to, that looks like the original problem. Matter of fact, it looks exactly like the original problem. This little integrand, this little part I have to take the derivative of down here looks exactly like the original problem. So let's go back to the original problem and do a little bit of substituting and see if we can figure something out here. So this is the original problem, and instead of just writing u dv, I'm going to write the original problem so that we can see everything. So this is the integral of e to the x cosine x. I'm going to have to write it a little small because I've got a lot to write across. Now this e to the x cosine x is equal to e to the x sine x minus this. Now I'm going to go back, I'm going to get this off of my other page. So I've got a minus here, minus that term is plus e to the x cosine x, and that's a plus, so when I put it with this minus, I get a minus the integral of e to the x cosine x dx. Okay. So this was the original problem. When I took by parts one time, I got this, so that just came straight down. I didn't have to worry about that. I took this one, went off and did by parts on this one, came back and got a negative this stuff. So I distributed the negative sign through there, and it made e to the x cosine x minus e to the x cosine x dx. And I got back to where I started from. But notice this is a minus. If this term, I don't know what this term is. Obviously, I'm having trouble finding what this is. But if this term, whatever it is the same as this term, I ought to be able to add this to both sides. It's a negative. If I take it over to the other side, it becomes a positive. And I get 2 times the integral of e to the x cosine x equals e to the x sine x plus e to the x cosine x. And now I can find this just by dividing both sides by 2. So I can get e to the x cosine x is equal to e to the x sine x plus e to the x cosine x all over 2. And of course you're sitting there waiting for me to forget my plus c. Now that's an interesting little problem. It happens occasionally. And one of the things that happens, one of the little indicators is that when you take the integration by parts the first time, you get something that is not more complicated but is very similar. Like this one to the original problem, we had the e to the x on both of them. We just switched cosine over to sine, and I happen to know that the sine was the derivative of the, the cosine is the derivative of the sine, the negative sign is the derivative of the cosine. So, it happens sometimes that by parts doesn't just pop right out the first time you try it. You might have to try it multiple times. Let me give you a problem that you can work on for a moment, and I'll let you try to set it up and take a shot at it. X to the fourth times the natural log of x dx. Now, if you use the ILATE, you've got what kind of an expression here? This is an algebraic function. This is a logarithmic function. So go back to your ILATE and follow the suggestion, and let me give you about a minute. Okay. The first thing we did then is we chose the u and the v. I let u be the natural log of x. I have the log function. I have the algebraic function. I let the natural log of x be the u function. Once I selected that of course left the dv to be the x to the fourth dx. Took the antiderivative here, add 1 divided by the new exponent. Took the derivative here. Remember, the derivative of the log is 1, the log of x is 1 over x dx. The next thing we needed to, that I like to do is to write down the formula and do my substitutions. Interesting little thing here. X cancels with the x to the fifth, makes an x to the fourth. So we have x to the fifth log x over 5 minus 1/5 the integral x to the fourth dx. Now, once you got that, this is quite easy to take the antiderivative of. The antiderivative of that is going to be x to the fifth over 5. We just did that up here to work on the x to the fourth. And we get x to the fifth log x over 5, that's an x, minus. Now, when I get this x to the fifth over 5, I'm going to multiply it by 1/5, so that means in the denominator I'm going to have a 25, x to the fifth over 25. And of course, since it's since there are no limits, plus C. I think that the reason I like this little example because of the way it cancels out in here. I just thought that was clever. I thought it was a neat little thing to look at, a neat little thing to pay attention to. This doesn't always come out to be just something that you take the antiderivative of. You can, oftentimes you get some neat little algebraic twist in there. And if you talk to most, I don't know, my impression, I don't know that studies have been on this, but my impression is that most of the problems of good students who do poorly in calculus is not because they can't do the calculus, it's because they either are slack or lax or just don't have enough good experience with manipulating the algebra. If you can manipulate the algebra well enough, the calculus is quite simple, more often than not. Okay. I'm going to do the same thing we just did. I'd like to give you a couple of problems that are very similar. Let's just do them one at a time. And I'm going to give you like a minute to do a little bit of practice on this one, the integral of x sine x dx. And then in a minute, I'm going to come along and give you the same, or something that looks very similar to this. It's going to be the integral of x squared sine x. And we'll see what happens to squaring a particular term in here in the methods of operation. In the methods of applying integration by parts. So let me give you this one, and again, you work a moment on that. Okay, I'm just going to write some stuff down here. You can sort of check along with what you've done, and I'll just write without talking too terribly much, I hope. That's a U. Okay, so I hope that one came out well for you. Again, when we took this, the two negatives made a positive. The antiderivative of the cosine is the negative sign, but since it was, excuse me, I said that backwards. The derivative of the sine is the cosine, so the integral of the cosine is the sine, and it's positive, so these two negatives just canceled each other out. I don't know, I was off in space for a minute. I was looking at these two as eyes, and that is the nose, and I just lost my train of thought there for a second. I guess I'm back. Woo! Okay. Sorry about that. Okay, the next one I want to look at is exactly the same as this one, except, that's why I like math teachers, exactly the same, except I'm going to make this an x squared. So what I would like you to do is write down the integral of x squared sine x dx, and let's slip through that one real quick. Let me give you again a few minutes. Now, if you've gotten to where I've gotten, you let u be the x squared and the dv is the sine x. Again, algebraic before trigonometric. To select for the u, we see the 2x dx and we see the minus cosine x, and we just do a substitution, do a little simplification here. This is all algebra. We get an x cosine x. And that's not something that we can easily take the antiderivative of. So what we can do on this one is a second by parts, where we let u be x and we let dv be the cosine of x. Now, I'm not going to ask you to do that one, but it will take a second. I'll just go ahead and give you the answer on this. But it would take a second integration by parts to do this part, so I'd need to go to another piece of paper, work this one out, and then come back in and substitute it. We would let the u be the x and the dv be the cosine x. Now this should work very similarly to the other one we had just a moment ago. Remember, the one we worked just a moment ago was not x squared sine x, it was x sine x. Well, this is x cosine x, so I would expect it to work in a very similar fashion. When you do all that magic, I'm going to draw the little line in here that says I've done a lot of magic and I've worked this problem earlier and I've already got the answer, so I'm just going to write it down for you. But you can figure out how I got there. I get minus x squared cosine x plus 2x sine x plus 2 cosine x plus a constant. So this comes from that part. You can see the 2, well, that 2 is going to be distributed over these two terms, and this is going to end up being both of those pieces. I'd like to just take a minute out with this one right here and look at something graphically. I'm not sure how many of you or how many of your students need to actually look at this, but I think it's good every once in a while to sort of do something comparatively graphically. Now, this proves it, so I don't have to do any more to a traditional mathematician, certainly. But you know, how do you get this intuitive feel? How do you work on that intuitive side of the mathematics, which I think is probably just as important. There was a study done, and I'm trying to remember where the study was. And of course, if you don't know, you always say it was either at Berkeley or Harvard or somewhere. There was a study done that tried to figure out how mathematicians created their theorems, how they not only came up with their ideas, but once they came up with their ideas, how did they figure out what to write down first, what to write down second? And the response was, or at least the thrust of the article was, that most of them use intuition. So you're using that intuitive logic rather than that deductive logic. And what's happening is the deductive logic is what's getting written down, but the intuitive logic is what you never see when you work the proof. So I think one of the things that you can work on, and you can work on it fairly well, I think, graphically, by looking at graphs, if students are understand what the graphs mean, that you can actually look at these things and help try to build some intuitive understanding. So what I would like to do is to look at these two things, look at this particular graph, and look at something associated with the graph of this and something associated with the graph of this. Now, I can graph both of those things individually, and I can compare the graphs. You know, if the function's increasing, if the function's decreasing. We did that about the third week, I think. It's not particularly easy to do that, especially on a graph that's probably a little difficult. It's a little tedious. But what I can do is on the TI-83, and I'm sure on other calculators, there's that numerical integration function, and we can graph the integral of this and then graph this and see if one ends up on top of the other. Now, it's going to take a while to substitute this into the equation, and if you ever used the numerical integration function, you will find out that it does work slowly at times. But let's go ahead and look at this one. Let me zoom in here. Okay. Clear that. Let's go to y equals, and I want to put in the function x squared times the sine of x and I want to do the numerical integration on that, so that would be under the math function, isn't it math 9, I believe? Math 9. If you mash the math button and you go down to the 9th option, it would be the integral of this function. So to get this function, I'm going to call that function's y1, so I'm going to go to vars, y vars, function, and I'm going to select y1, comma. Now, this requires 4 components. This argument requires 4 components. The first one is the function. I've got that. The second one is your dx, so I have to put in x to say that x is the variable I'm working with. And then the last 2 parts, generally this does a definite integral. That actually evaluates and gives you values, and you put your first value and your starting value and your ending value. So I believe what we can do here, instead of doing that, we can go, instead of from 0 to 5 or from 0 to 7, we go from 0 to x. And I believe, at least last night when I was doing this again, that should in fact work. Now, this is the one I want to graph, not this one. So I'm going to go back up to the first one, and And if you arrow back to the equals mark and hit the enter, then you take that bold off the equals, and that one is in there, and you can use it. It's just not going to graph on the screen. Now, the one that I want to compare that to was the one that I got as the answer. So let's go back and look at the numerical value, the function that I got that was the antiderivative. So that's what I'm going to put in for y3. Okay. So let me zoom back. Minus x squared cosine x plus 2x sine x plus 2 cosine, I've lost my place here, x. Now, I don't have a constant to add, so I'm just going to add the 0. Did I put the negative cosine squared in there? Okay. Another thing that I could do, instead of comparing the integral of this one, I just thought about this, instead of comparing the integral of this one to this one, I can compare this one to the derivative of that one. I could do either way, and Math 8 will give you the numerical derivative, and you do it very similarly. So let's go to, let me see if I can find some type of range for this. Let's just do, let's see what happens with a zoom. Where is it? Zoom 7? Zoom 7 is the trig, since we've got some trig functions in here. Okay, I've typed in something wrong. Oh. After my 0, I didn't put a comma. 0, comma, x. I hope that's what it was. Okay, I see my little stuff up here. So obviously I don't have a particularly good, well, I got excited about that. It's coming right up here. So this is probably not a particularly good screen to look at this function because a lot of stuff's missing. So let's see what happens to it. Actually, let me not do that. Let me stop it and let me zoom out and see if I can get a better graph. Again, this does take a while to graph, mostly because it's doing an integral, then it's substituting in, and so it's doing like 4 or 5 steps to find one point. Oops, I forgot something. Darn it. How am I going to tell when the second graphs over the top of the first one? Yeah, and I should have done the thicker one. I forgot to do that. If you go back to your y equals, and I'll do this. If you go back to your y equals, you want to make the two styles of graph different.
I did mine.
Oh, okay. I've got another little thing. It's still graphing. Oh, well, it's not matching. Okay. Let me see, they're not matching there?
Oh, no.
Okay, wait a minute.
I didn't do anything there. I just did okay. I didn't do it.
Oh, you did the derivative one. Okay, you're graphing different things. You're graphing the integral of that one and the derivative of that one.
I hope that's what we're supposed to do. Right.
Well, mine aren't matching either, so what have I done wrong? Have I put the function in wrong? because mine didn't match. Oh boy. So you can absolutely tell that, oh, God, yeah, duh. Okay. I just said that. I said that a while ago. I said, okay, duh. I'm having a good day today. I hope you are too. If we zoom out, these two things will be off by constant. It looks like it's very possible that if I slide this up by 2, it's going to match. So let me go back to this right here without spending too much time on it. Just remind you that if you go back to this function right here and you start pressing, if you get your cursor right here on that little symbol in front of the Y and you start mashing the equals button, you can get a bow line, you can get a shade in one side of the line, shade in below it. That will give you a little bubble that you can follow around, a little tracer bubble that you can follow how the graph is being created. And that last one will actually leave the trail. This one, just the circle, you'll see the bubble moving around, but you won't see the trail. So, and then after about those, it starts cycling through the 4 or 5 options there. Okay, I want to go back up to this one. Let's see if I can do this, and it looked like it was off by about 2 because those little things. So let me put a -2 here. Now I'm playing with this one. So let's zoom out one more time. Let's zoom out and get much better. Whoops. So obviously I've done something wrong. Well, you can tell this is live and not taped and corrected. So I've got something somewhere that I've done wrong, and it's not coming to me real quickly. Let me look at my functions for just a second. Let me stop them, go back and look at my functions. Maybe that wasn't what I wanted to do. Okay. The original was x squared times the sine of x. I hope you're not looking at this thing saying, God, dummy, why did you do that? Okay, minus x squared cosine x plus 2x sine x plus 2 cosine x. Now, I told you that was the answer, and that's what I've got written down. Minus x squared cosine x plus 2x times the sine of x plus 2 times the cosine of x. Oh, I didn't want number 1 on. Duh. Okay, see? These are the two I wanted to graph right here. I wanted to graph the function and that. So now let's try it. I thought that first one graphed too easily, too quickly. Okay. So we're going to get it. Okay. So this should be the FNINT. This is Y2 graphing. It's got a nice little fin. It's got the graphing thickness.
If you want to jump ahead.
Okay. And now you see the lips. Now you don't. So we won't spend the next 10 minutes waiting for it to graph. You will see that finally, after I figure out what's going on, it will graph on top of itself. So the two functions do graph. They always told me in graduate school that, or in every teacher thing, it's always good for students to see their professor struggle with problems. Well, I didn't mean for you to see me struggle this much. Oops. I swear I worked that problem last night before I came to school. The next little thing I want to look at in terms of integration by parts and use substitution and some things like that. I want to look at a couple of things that pop up quite often. Okay, it doesn't match, but I didn't put the minus, took the -2 off. Okay.